Okay, this is the module on double integration. This is the first new thing we're doing after we've now left contour integrals or line integrals, path integrals, that sort of thing. In some ways, this will be easier, I think, than line integration, because I think it's easier to understand what we're doing. But it gets technically more, the problems get longer because you're just doing two integrations in a row, and they can be not super complicated, but a little bit more complicated than what you did last year in first year. So when we're doing double integration, we assume, this is the kind of problem, this is an example. You'll write it like a double integral, so two integral signs. You'll have usually some symbol says R or A or something that suggests that that's the region over which you're going to integrate. You have some function of x and y in general. Nothing sacred or important about x and y. We tend to use that first, but it could be any two variable combination. And then an area element. So normally, before we did line integrals, we had a function we're integrating, and then you had some step increment. Now we have a function we're integrating in some area increment under the curve that we're considering, the function over. Okay. We're going to do this in Cartesian coordinates at this point, but the module after this, not next class, but later this week, we'll move to cylindrical coordinates or polar coordinates in 2D. Okay. Now the picture, like the geometric interpretation, right, is that we've got something like this. Okay, here's x, here's y. This is the plane over which we're integrating. Okay, there's some region R, and then we have z equals some function x over y as a height over, or under for that matter, but let's just call it over this surface. Okay, and that can be something, okay, over top of R. And when we consider a little piece of f of xy, there's an area increment under which, and we're basically calculating the volume of that column. So if your area element, then you think of the height of the function above it, that has a volume, and we're going to move around this R, summing those all up. So it's, and you knew that already. That's the simple interpretation of this thing. So again, compared to line integration, where it was harder to understand what we're doing because we're just summing along a line, now we're summing over a region, and it almost is easier to visualize, I would say. Now, there are a couple properties of double integration, none of which are surprising. It's a linear operation. So when you take a double integral, we usually say a times f plus b times g, right? dA, where a and b are constants and f and g are functions. This is just a times the double integral of f dA plus b times the double integral of g dA. Just like, so that's linearity. It's a linear operation. And we'll do that sometimes. We'll have a region we're integrating over, we're going to break it into two pieces, maybe. We have constants inside, we're going to move them outside. That's the usual stuff. It's a natural thing, you almost don't need to think of it as a separate property, you're used to that. It's more when we have operations that aren't linear that we have to pay attention. Okay, and then we have this union idea, where if I have an integration of over R, well, that I can break that into integrations over subregions as long as R1 plus R2 equals R, right? So if I had this region here and I broke this into this, and this was R1 and this was R2, I could do each integration separately, then sum them together. And we do that a lot of times to make things simpler. Okay, now, so when we get to doing these things, the first thing that we need to do is make a decision or sort of a strategy in terms of doing the integral. And so we're going to have a choice in a double integration. And let's look at this example here. Basically, when we're doing integration, we call this sort of, what's the word I use? Iterated integration. When we think of x and y, for example, we're going to integrate either x first and then do y, or y first and then do x. And which we do, it shouldn't matter in terms of the result. Usually one way is easier, Sometimes they're both very easy, sometimes they're both very hard, but often one way is easier. Sometimes, and actually in this first example I'll show you, sometimes one way is not possible. That's rarer, but it's possible. Now, if we just look at this area here that we're going to integrate over, you can sort of see what I mean. I'm going to integrate this function, xy squared, over top of this thing. Okay, so xy squared is sitting out of the board here somewhere. And we have a choice whether we're going to say, I'm going to integrate in the vertical direction, so I'm going to integrate along y, and I'm going to compress this thing down to be only a function of x. So I do y first, then I'm left with x, then I integrate x. Okay? And this will be more obvious when we do the first example. Or I might integrate along x first, so squeeze the dimension this way, be left with a function of y, and then integrate y. Okay? The textbook talks about, and I will cease to use this terminology pretty soon. About two different types. So it calls type 1, where you're going to integrate along y first and then get a function of x, and then integrate that. And type 2 is the opposite. X first, then y. Now sometimes it's kind of obvious, and I have a diagram in the notes about this, but if you had this, so if you imagine you have, this is x, y, so some specified limits in x and some functional limits in y, where this is g1 at x, and this is g2 at x, then this would be this type 1. And when we integrate that, what we would be saying is, I'm going to take the x integral last, the y integral first, like so. And so this is important notation. This is this iterated integration. So the idea is the double integral, one of the integration signs is for x, one's for y. Okay? And what we'll do is we're going to sort of bracket this. So I'm going to do this integral first. So I'm going to look at the limits of the region for y first. So in this case here, the limit for y is this function to this function. So it starts at g1 of x and goes to g2 of x. The point is, and the limits are functions of x in general. Okay? If this was a square rectangle, both limits would be constants and it wouldn't matter. But here, this is a function of x, this is a function of x. So I'm going to do that integral first. And I put the dy in there first. It tells me that I'm doing this integral with y. So I find the antiderivative of this function, then you evaluate it at these two functions, and when I'm done, I'll have a function of x. And then we do a 1D integration of x to get the final answer. The final answer is still a number, right? We're doing definite integration, and so we're going to end up with a number, not a function of x or y when we're done. The type 2 region, you can sort of figure out what that would look like here, might look like this. So similarly, okay, C and D for y and x. Okay, and I got some h1 and h2 functions of y. So this guy, when I do it, would look like, I'm doing x first, oh, sorry, h1 of y, h2 of y, my function of x and y, integrating with respect to x, then integrating with respect to y. So notice the difference. When I do this antiderivative of x, my limits are functions of y. So when we're done, this whole thing only depends on y. When I was done here, this is only x. Okay? So that's the choice we have. We have to decide whether we're going to represent this thing or try to approach this thing first in x and then y, or first in y and then x. So let's do this first example that I showed us. We'll try it both ways. We'll see that one of the ways works and one of the ways doesn't work. Okay. Okay, so let's just continue on with this example here. Okay. This is going to be the value I want. I want the value of this integral over this region here. And this region is, we would say it is the region in the first quadrant. Okay, so it's limited by y equals 0 and x equals 0. Okay. The bottom limit along y is y equals x squared. Okay. The top limit along y is y equals 4. So we could do this either way. Let's try type 1. Okay, so we're going to integrate out y. So we're going to integrate in this direction first, and then we'll integrate along x. And we'll see there's a problem right away. And then we'll show it the other way. Okay, but first of all, we're going to integrate y, then x. Okay, so that means our limits of x are this, right? 0, 2. Sorry, this is obvious. This is 2 because this function is y equals x squared. Y equals x squared crosses y equal 4 at x equals 2. Okay, so x goes from 0 to 2. What does y go from? Well, at every value, y goes from x squared and goes up to 4. Okay? So, this is the thing. The limits of y are functions of x. They don't have to be explicit functions of x, like 4 is a constant, but we think of this still as in general sort of a function of x. Okay? So those are our limits. So let's set up the double integral. The double integral will look like this. Okay, so r x e to the y squared dA. Okay, so now I'll set up like we showed, the x limits first, the y limits second, e to the y, dy, dx. Okay, now when we do this, now we just focus on this 1D integral. X is a constant with respect to y, so this becomes the same as 0 to x, to bring it out. Now I have x squared 4 e to the y. Oh yeah, y squared. Y squared dy dx. And I focus all my attention on this. And right away, this is the problem. Okay, and this is a funny problem in this particular example, but and we've mentioned this in class before, there is no antiderivative for e to the y squared. Okay? We can't solve this. Okay? You could numerically solve it, but analytically we can't solve this. Okay? Because there's no antiderivative for e to the y squared. You can't do it. If you try for a minute, you'll realize that pretty quick. So this is a no-go. Okay? It's not obvious. It's not always this obvious, and if one fails, usually the case is one way is just harder than the other, not impossible like this. But in this case, we run into this problem. So when this happens in double integration, you're prepared for this, that maybe the way I chose is not going to work. So if you run into a problem or it gets really complicated, you just stop and set up the other way and see. And with experience, you start to get a sense of which way is going to be easier or harder. But it's not easy to tell, right? It's not easy to tell always when an integral is going to be difficult to do or not. Okay. So let's convert this now. So let's go x first, then y. Okay. So if we think of this then, the y limits go from 0 to 4. And the x limit goes from 0 to the square root of y. If I solve this, this means that x equals square root y. I know it's plus or minus square root. That would be this guy down here. Since we're in the first quadrant, we only have the plus case. So this means that x goes between 0 and the square root of y. So you see the x limits are functions of y, the y limits are constants. Okay. So now we set this guy up. Okay, so my r x e to the y squared dA becomes 0 to 4, y is on the outside, and then 0 to the square root of y, x e to the y squared dx dy. The convention is that when you have double integrals in higher orders, it's almost like bracketing. So when you write your dx's and dy's together, the first one is the first integral, the outer one is the outer integral. If we have a third one, the third one would be the further outer integral. That's the typical thing to do. There are other conventions we'll talk a little bit about as we go, but that's the pretty standard one. So now we pull out, we're trying to do x first. So everything that's not a function of x, we take outside. And now you can sort of see how we make, now this one, we have somewhere to go. e to the y squared is constant with respect to x. And then I have 0 square root y, x, dx, dy. Okay, so now we have somewhere to go. It's not totally obvious. We still have this thing hanging around, but you'll see how we set ourselves up for a substitution. Okay, so this becomes, okay, so for 0 e to the y squared, this is just x squared over 2, evaluated at square root y, just like 0, or just like before. We do everything like before, but now our limits are functions of y in general. Okay, here I'm just gonna, so this becomes x squared root y becomes y over 2, and 0, 0. So this becomes 1 over 2, taking the 1 over 2 out, 0 to the 4, y, e to the y squared, ey. Okay. So now we do a second integral. But this is now just, we could have given ourselves this problem last year. So now we've taken this 2D problem, we've separated out one, did it, and when we're done, we have what would be a first year integral. Okay? And we'll just do this one pretty quickly, but you might know how to do it. It's set up for substitution now. So now we have a way to deal with this because we're gonna do a substitution to get rid of this y squared. Now when I'm doing this sort of thing, I usually say, okay, let me just calculate this thing. So the antiderivative, I'm just going to, rather than have the full, just look at this for a second. Don't worry about the limits of integration. So in this kind of case, you'd let u equal y squared. That means du dy is 2y, which means dy is 1/2 dy is 1/2. Sorry. Du equals 2y dy. Okay, so 1/2 du equals y dy. I want to get y dy because that's what I've got here. So I've got here. Okay, so if that's the case, then this thing turns into 1/2 antiderivative of e to the u du, right? Because u equals y squared, so e to the u. Y dy is 1/2 du, so this thing just becomes 1 over 2 e to the u. And now we put the values back in, so this is 1 over 2 e to the y squared. Okay, so that's the antiderivative of that. So we'll put that into there now. So just remember this 1/2 ey squared. Okay, so this integral then, my original integral, becomes 1 over 2, then the one I just had at the limits. Right? This is the integral we solved up there. This is what we have now. This becomes 1 over 4 e to the 16 minus e to the 0. So this becomes 1 over 4 e to the 16 minus 1. Bizarre number in the end, but that is the answer. Okay. So this, so that's our example of our double integral. They're all kind of like this. That one's not trivial. There is a more trivial case where the limits are constants in both directions. But this is the approach. You have to, so one thing about before, when we did the contour integrals and the path integrals, I said you should sketch the contour. And we strongly suggested it. And I still think you kind of have to. Here, you have to sketch R. If you can't visualize R, you can't do the problem. And some questions even in the back of this section, and this is section 10, so chapter 9, section 10 of the textbook. There are problems in the back that just say, sketch the region of integration, okay? Because you have to be able to do that. And once you sketch it, you can then discern, well, which way am I going to try to do this? Or what does it mean to do it one way or the other? And then, so we sketch the region, then we choose our coordinate system. These ones are pretty much chosen for us. And then we have two approaches. And it's not easy to say which is always simplest. Generally, if one of the variables is limited by constants and the other one is limited purely by functions, you kind of know which way you have to do it. You have to do the one with functions first and then the constants. But if some of them have an option, like this one had an option, then you just kind of have to try it both ways. Usually they'll both work. One's maybe just a little easier than the other, but it's going to be a little bit of experience. Okay, so that's double integration. We're going to do this for a little bit. Then pretty soon we're going to switch to a different coordinate system and look at double integration in polar coordinates. And then we'll move on to surface integration. Then after surface integration, other coordinates, then we go into volume integration. And while we're doing these, sometimes we're going to be integrating normal scalar functions, and sometimes we're going to integrate vector functions. Once we have all that together, we can put together the big theorems of the course. So Green's theorem in the plane, so Green's theorem, Stokes' theorem, and the divergence theorem. Okay.